Lesson 91, you'll notice it says product and difference indeterminate forms. We talked about indeterminate form, I don't know, a couple weeks ago now. When did we talk about indeterminate forms? When we learned what rule? The hospital rule, says Daryl. I'm going to say L'Hopital's rule, but yes, I agree. Okay, so the idea today, we're still using L'Hopital's. The indeterminate forms we learned in the past were if it was 0 over 0 or infinity over infinity. And then we take the derivative of both, reapply limits until we can get something to work. Okay, so the indeterminate forms we're looking at today are, instead of being 0 over 0 or infinity over infinity, are, okay, what if you have 0 times infinity, is what that's supposed to say. Or what if you have infinity minus infinity? Those are the two new indeterminate forms we're looking at. And as it says there, we already know 0 over 0, infinity over infinity. Note, it says, use the same L'Hopital's rule, just a few algebraic tricks. So let's look at example 1. Example 1 asks us to evaluate the limit as x approaches 0 of x times cosecant x. Well, if we try and plug 0 in right there, as is, x is 0. What about cosecant of 0? Can you visualize what's happening there? No, cosecant. So cosecant would be based on the sine curve, right? And if it's based on the sine curve, the parabola there would be going up. Yes? Yeah, the parabola would be going up, or at least from the right side. It would be going up, which is up to infinity. Okay, so again, the idea here is 0 times infinity, indeterminate form. Now, we don't have a L'Hopital's rule, though, that says what to do if they multiply. So, it talks about algebraic tricks. Our L'Hopital's rule has the limit in a fraction. Any thoughts about x times cosecant x as a fraction? X over sine x. Cosecant is the reciprocal of sine. So what if I make this instead the limit as x approaches 0 as x of x over sine x? So now what happens when you plug in 0? X is 0 and sine of 0 is 0. And so, since you get 0 over 0, that's one of our traditional L'Hopital forms, isn't it? If the limit equals equal to 0 over 0, we take the derivative of the top and the derivative of the numerator. So, again, it's... Huh?
Is it the top and the numerator the same?
Yes. Is that what I said? Okay, you guys know what I meant is what I'm going to hope here. The derivative of the numerator and then the derivative of the denominator. Or the derivative of the top and the derivative of the bottom. Okay, so what is the derivative of x? 1. What is the derivative of sine x? Cosine x. And now, reevaluate. On top, 1 is 1, so it can't be 0 over 0 this time. What is cosine of 0?
1.
1. And what is 1 over 1?
1.
1. So, using that L'Hopital's rule, again, algebraic tricks to make it be a fraction. That's going to be the key today, is you need to make them be a fraction, and then you can apply L'Hopital's most likely. Questions?
I got to say 1 a lot in that problem.
Okay, example 2. The limit as x approaches infinity of e to the negative x natural log of x. What are your thoughts here?
As natural log goes right to infinity, it'll go up to infinity.
Yes, as natural log approaches infinity, or as x approaches infinity, the natural log of x approaches infinity. What about that e to the negative x?
Is it flipped across the y-axis?
If you're thinking in terms of the graph, yes, it would be flipped across the y-axis.
You could also make it a power of ln x.
As it is approaching infinity, then it would be approaching 0.
Okay. Yeah, the key is as it approaches infinity, it's going to be 0. And so Daryl went with the graph. I went with, okay, it's e to the negative x, so that's 1 over e to the x. And e to the infinity, so it's 1 over an increasingly larger number, and 1 over infinity is 0. I can go with the, So regardless, we end up with 0 times infinity, which is one of our new indeterminate forms, right? And I kind of already started doing it. We need to make this a fraction. What do you know about e to the negative x times ln x?
ln x over e to the x.
Natural log of x stays on top. E to the negative x, to make that positive exponent, it's e to the positive x in the denominator. And so now, verify that we need to use L'Hopital's. Natural log, as x gets bigger, the natural log gets bigger. E to the infinity, so e to an ever-increasing power, that is going to be infinity over infinity. So, because we have that indeterminate form, we're going to apply L'Hopital's rule. Limit as x approaches infinity. What's the derivative of natural log of x? 1 over x. What's the derivative of e to the x? E to the x. So I end up with 1 over x over e to the x. Now, you can work with this as is. If you don't like that fraction within a fraction, then keep in mind 1 over x divided by e to the x could also be rewritten in a nicer fraction, which is 1 over x e to the x. And I don't know if you require that for your brain to process this or not. And you could plug in infinity in either one of these. If we use the one I just did, it's going to be 1 over x times e to the x as x approaches infinity. What's happening? Yeah, they're both infinity. And infinity times infinity is still just going to be infinity, right? What is 1 over infinity equivalent to?
0.
It's getting closer and closer to 0, isn't it? A solid 1 in an increasingly bigger denominator is getting closer and closer to 0.
At the start, since 0 times anything is 0, whenever we take the limit they give us and we get 0 times infinity, can we just go to 0?
I don't think you can. I think there's exceptions to that rule. Because they wouldn't call it an indeterminate form if 0 times infinity always ended up being 0. You see what I'm saying there? I don't know. I don't have the counterexample to prove myself right now.
Because if somebody says they're going to give me infinitely more one. I have my pockets right now. I have none in my pockets, so I'm not going to get anyone. It's going to be 0.
Well, but I think it depends which one then moves to the denominator.
There's probably going to be an example in the homework where it doesn't turn out to be 0.
Yeah. So, and real quick before I move on, if you left it in this form, it would have been 1 over infinity, which is 0, over infinity. And 0 over infinity would have also given me 0. Okay?
So you can divide 0 by infinity, you just can't multiply 0 by infinity.
It's the different, yeah, it's considered an indeterminate form there. Okay, ready for example 3? You can kind of guess what's going to happen here. Limit as x approaches 0 of 1 over x minus 1 over sine x.
I'm not a gambling person, but I'm a wager we get an indeterminate.
Okay, and which indeterminate form are we going to get here?
Probably infinity minus infinity.
Yeah, infinity minus infinity is what this one works out to be because it's 1 over 0 minus another 1 over 0. Okay, on the last two, there was something pretty obvious to flip down and make the denominator so we had a fraction. In this case, we already have fractions being subtracted. What do we need to do with this? Instead of having two fractions being subtracted, we need to make this into not two fractions, but one fraction. Because our goal is to get one of the indeterminate forms we can work with, 0 over 0 or infinity over infinity. So how do we make this into one fraction? I would not
Multiply by each other's denominator.
Okay. So I've heard two different options here, and I know half of you have heard one and not the other. But so I heard something on virtual about cosecant x, flipping that sign up and making it cosecant x, which you could do. My brain just works better in sine. The other option, I mean, regardless, we're still going to have a common denominator and put this together as one fraction. In my brain, it would work better to put x and sine x together as my common denominator. Again, and I guess I'm stating because I work better with sine than cosecant, especially if I'm going to have to take the derivative. I'd rather take derivative of sine than cosecant. So what I would go with is common denominator is x sine x, right? If my first fraction was x, we're going to have to multiply that numerator by sine x. If my second fraction has a denominator of sine x, we're going to have to multiply by x to get that common denominator. So we end up with sine x minus x over x sine x. Are we okay with that? Now, check yourself out before you just jump right into L'Hopital's. Is it an indeterminate form still? Yeah, if you plug in 0, you're going to end up with 0 over 0, which means we need to apply L'Hopital's. So, limit as x approaches 0. What is the derivative of sine x minus x? Cosine x minus 1. What is the derivative of x sine x?
Sine x plus x cosine x.
Yeah, we don't want to hear this, but what has to happen when you see the x sine x? Product rule, right? There's two pieces, two functions being multiplied together, so product rule.
At least this one isn't that bad, though.
No, it's not a bad product rule. So the derivative of x is 1, keep the sine x. Plus, this time we're going to keep the x, and the derivative of sine x is cosine x. So, now what happens when I plug in 0? Okay. On top, cosine of 0 is 1. So 1 minus 1 is 0 on top. Denominator, sine of 0 plus 0 times cosine of 0. 0 over 0 again.
I'm sure glad we didn't go cosecant route now. Well, derivative is okay. See what gets better.
Okay, and that is a valid point. I mean, we're taking a lot of derivatives here. So, and this is why I advised against cosecant. Because we're not big fans of the derivative of cosecant anyways, and we'd be messing with cosecants and cotangents. Okay, so L'Hopital we go again. The limit as x approaches infinity, 0. What is the derivative of cosine x minus 1? Negative sine x. Okay. Denominator. What is the derivative of sine x? Cosine x. Plus, what is the derivative of x cosine x? Another product rule. So the derivative of x is 1. Keep the cosine x. Plus, this time we're going to keep the x. What's the derivative of cosine x? Negative sine x. So this is negative x sine x. Okay. Numerator. Negative sine of 0. Still 0. Denominator. Cosine of 0. 1. Plus cosine of 0. 1. Minus x, or 0 times sine 0. 0. What do I end up with? 0 over 2, which is 0. Man, that would have been a lot easier with a graphing calculator and just checking my graph out of that one. Would have been a lot quicker, that is. Okay. Let's try another one. Example 4.
Is that 0 from the left or infinity?
That is a good question. I'm so confused about my notes here. That is supposed to be, it looks like it says 0 from the left, but in my notes I have it written as 0 from the right. So let's go as x approaches 0 from the right. Oh yeah, it has to be from the right now that I look at it. Because we're talking about square roots. The square root does not exist on the left side of the graph. So, okay. 1 over x minus 1 over square root of x. What do you know right now if you plug in 0?
You get infinity times infinity minus infinity.
Okay. This is back to the infinity minus infinity, because it's 1 over 0.
How do they decide that 1 over 0 is infinity? Since it's undefined, do you just assume it's infinity because there's an asymptote or something?
I think so. I mean, that, there has to be either a whole or an asymptote there. And there's usually an asymptote unless there's a equivalent factor on top, so some kind of infinity most likely. Or possibly an undefined if it goes, this one's just from the right. But, okay, what needs to happen here?
Common denominator.
Common denominator. What common denominator would you guys like?
X square root of x.
I could go with x square root of x.
Or
I'm not opposed. I see something a little neater if you want to go for it.
x times x to the 1/2.
No?
Could we make that x to the positive 1/2? Because wait,
I'm trying to decide if we go the x square root of x, how messy it ends up, or x to the x times x to the 1/2. But I'm looking at that first denominator of x. It's just a nice, neat x, yes? What do you know about the square root of x? Can you get the square root of x to become x?
Squared.
Okay, don't think square it though. What are you doing when you square it?
Multiplying it by itself.
Multiplying it by itself. So if you multiply square root of x by square root of x, you get x, yes? Which, and the reason I said don't think squaring it, because it's the whole whatever you multiply the bottom by, you multiply the top by, which means we're going to be multiplying that numerator by square root of x. You see how I'm doing this? So if I rewrite this, the limit as x approaches 0 from the right, and I'm going to leave it as two fractions for a moment, 1 over x minus square root of x over x. And I'm not saying we couldn't have gone x square root of x as your common denominator. I'm just trying to make it a little bit, should I use the word prettier for you? A little bit nicer. So now, can you combine this easier into one fraction? Limit as x approaches 0 from the right. What is this as one fraction? Common denominator of x. And so 1 minus square root of x all over x. Which, if we had gone the square root of x route, your fraction would simplify to this. It would just not look as pretty for the moment. Okay. What happens when I start putting 0 in here?
You get 0 in the denominator, which you can't do.
Well,
When you kind of can, just stop. Like,
we get 0 in the denominator. What's that numerator come out to be? 1 minus 0, which is 1. What is 1 divided by 0 defined to be? Infinity. So it does happen sometimes. And this is because we're approaching 0 from the right. If we were trying to approach 0 from both sides, we might have to, rediscuss this, whatever. But because we're approaching 0 just from the right, we can do that. Questions there? Okay. Let's try example 5 then. Evaluate the limit. This is as x approaches 0 of negative 1 over x minus cosecant x.
first thing we could do is change negative cosecant x into negative 1 over sine x.
Okay. So options do include taking that cosecant x and changing it to 1 over sine x. Now, I'm trying to process for a moment. Why did I do this the way I did this? I'm not disagreeing with you, but that's not what I did in my notes, and I can't.
You can't figure out why you did the different.
Why did I go a different direction on this one? That's why I'm struck. Like, my brain is not quickly grasping why.
To prepare us for a different direction.
Okay, so okay, we would be fine. Okay. But still, why didn't I go that direction? Okay, my brain's. I'm gonna have to look into this here in a moment. Can't remember why I didn't go this direction. So, okay. Whether we think cosecant or, I'm keeping in mind the 1 over sine x. I, again, not disagree. What happens when we plug 0 in? 1 over, it's the negative, but 1 over 0 is going to be thought of as what? Infinity. Now, cosecant, if we think about it as 1 over sine, that's 1 over 0, which is also infinity. Now, before I go that direction, though, let's think about cosecant for a moment. Can you guys, and I started to talk about this a little bit earlier, but can you visualize what the cosecant graph looks like? Cosecant graph is based on what? The sine graph. And at the origin, the sine graph goes up on the right and it would go down on the left if we did that, right? And what's cosecant say about that? Cosecant is at every 0 there's an asymptote, and at every min or max there's a parabola. Does that sound familiar? My pre-calc kids just quizzed on this today. Now, with that being in mind, okay, so there is an asymptote here at 0. This is just as x approaches 0. It doesn't specify left or right. What is this graph doing as x approaches 0 here? It goes opposite directions. So officially at that exact point, it's undefined, isn't it? And so this is where instead of using L'Hopital's, and again, I'm struggling with how do you know that if you change to sine? The brain's not grasping. I'll look in the book here in a moment. Okay? But because of this right here, I broke it into, okay, what happens when it's undefined and goes opposite directions? We need to investigate it individually, right? We investigate it from the left, from the right. If those match, then we have a consistent answer. If they don't match, it's undefined. And so, if we break this up and look at it, the limit as x approaches 0 from the right of negative 1 over x minus cosecant x, and the limit as x approaches 0 from the left of negative 1 over x minus cosecant x. What happens with these right here? Do they come out to be the same when we look at them individually? So 0 from the right. Negative 1 over x. So the negative of 1 over positive values. What's that going to approach? It's the negative of what's 1 over 0 approach? Infinity. And it's because it's 1 over positive values, it's 1 over, or it's positive infinity, right? Minus, what does cosecant of 0 do from the right? It goes where? Up to positive infinity. So from the right, it's negative infinity minus infinity, which still puts us at what kind of infinity? But negative infinity. When you're already in negative infinity, you're subtracting more infinity, you're in negative infinity. Now consider this from the left. It's the negative of 1 over x. So the negative of 1 over negative values. 1 over negative values is going to approach what? Well,
It's going to approach negative infinity, but the negative out front.
okay, yes. So the negative of negative infinity, which does turn around and make it positive infinity. Okay, minus cosecant. So what is 0 as we approach 0 from the left? This time we're going where? Negative infinity. Negative of negative infinity minus negative infinity is what? Positive infinity.
And beyond.
Not Toy Story. Now, do my limits match? No. Okay. Even once, we already knew they didn't match on cosecant. When we start putting them together and try and match, they still don't match. So what does that say about this limit if they don't match? The limit as a whole does not exist, because if we just talk about the limit as x approaches 0, it does two different things. One from the left and one from the right. Now, if we talked about left separately and right separately, obviously we can do that. I want to check something. I do have a couple problems to write down for you there. See, they just automatically started looking at left and right hand limits. But how would you have known that if you changed it into cos or sine? I guess that's one of those when you're looking at that limit, you don't want to change it until we know we have an indeterminate form. And maybe that's what I should be saying there. Because, you have to check and make sure you have that indeterminate form before you change it. That's the best. I need to read up on that problem a little bit because I don't have a good answer there. Okay. I have two problems that change from 286s that change and 287s that change. So number 1 and number 19 are going to become numbers 13 and 14 from 86. And then we have 15 and 16 that are going to become numbers 3 and 4 from 87. And am I on the screen? I am.
So last night's homework, I just did 22 to 25, I think. I didn't change them. Because they were things that we could do.
Why did I change them then? There was some reason I changed them, but I don't remember what.
Because I was looking through it and I was like, oh, I know how to do all this. Except for maybe like one or two of the problems. I'm not sure.
It could just be that the 5, 6, 7, 8 were something I wanted you to look at. I don't know until I glance over and see what they were. But I agree, one of them is partially from 86, but they're not necessarily things you totally can't do. But okay, no, don't turn off screen. Okay.
I just need to start writing in what changes and doesn't at the very beginning.